Hello everyone, my name is Alessandro Cornacchia and I'm a PhD student from Politecnico di Torino. Thank you for the opportunity of being here. Today I'm going to present you our work on a traffic-aware perspective on network disaggregated sketches. Well, nowadays network telemetry is a fundamental task for successfully running the network. Network operators indeed demand more and more telemetry capabilities in order to understand what's really going on in the network, detect anomalies, and plan future infrastructure upgrades. For example, in a data center network, when a switch becomes overloaded, packets passing through that switch starts experiencing increased delays or drops, degrading application performances. In this case, the operator would really like to find out which are the culprit flows in order to take proper countermeasures, such as rerouting. In order to do so, it is not enough to measure packet statistics, but we really need to monitor flow level metrics. For example, the number of unique flows, the flow size distribution, or detect the heavy ether flows. In general, we think that the measurement system must simultaneously satisfy some key requirements. First, it must provide highly accurate results, meaning that the answers to user queries must agree with reality. Second, it must ensure high flow coverage, meaning that it must avoid that some flows goes undetected. For this reason, some legacy solutions based on sampling in order to keep up with line rates like traditional net flow fall short. Finally, a good design must be lightweight in terms of computation, storage, and bandwidth, which is obviously in contrast with the two previous requirements. Well, the state-of-the-art solution that meet the previous requirements are the so-called sketches. Sketches are probabilistic data structures, which means they are not exact, but only provide approximate results that usually are within some provable bounds. However, their main advantage is that they are extremely lightweight in terms of resource footprint. In particular, the required memory entries for a sketch in order to operate with an acceptable accuracy is much smaller than the total number of flows. Also, since they apply very simple operations on a per packet basis, they can run at line rate without the need of sampling, thus meeting also the high coverage constraint. Here we have an example of a sketch data structure. The memory on a switch is essentially organized into different arrays of counters. Now, suppose that we want to use the sketch for estimating the flow size. For each new packet, we have to execute the update operation. First, we extract the flow identifier f, and we apply an hash function in order to get access to a location on the array of counters. For example, in this case, we get access to the second location, and we increase the corresponding counter by 1. Then we repeat the same operation for all the rows with independent hash functions. Now, suppose that the network manager wants to query the size of f. This operation consists on just taking the minimum. Indeed, since the number of counters is much less than the number of total flows, different flows will obviously collide on the same counter. And by taking the minimum, we mitigate the impact of hash collisions. Well, once we have atomic sketches, still they should be deployed network-wide. And the standard approach to doing this is to keep network switches with their own atomic sketch. And in this configuration, all the sketches are independent on each other. Then a central controller periodically fetches the counters and put them together in order to answer user queries. Of course, in this case, we should take care not to counting a flow twice. It's important also to note that with this approach, the available memory budget, that is the number of counters at each switch, is partitioned into different rows corresponding to different hash functions, as in standard atomic sketches. Instead, an alternative approach has been recently proposed. This new scheme is based on the concept of network disaggregation. Disaggregation means splitting a logical sketch into multiple fragments and deploy the fragments on network switches. Now, the final sketch is constructed just by reassembling fragments encountered along a given flow path. Indeed, notice that now the available memory is organized just into a single hash function, as we can see here. The update operation is performed packet by packet, just updating fragments along the path. The current minimum value is piggybacked on the packet for the query operation. This solution was essentially shown to outperform the previous approach. However, In our work, we claim that this design is far from being optimal. In particular, we claim that flows shouldn't be counted on all fragments along the flow path. And the problem in doing so is that since now the fragments are shared, of course, among crossing paths, at each update operation, we generate interference to flows of other paths. We refer to this concept as counter pollution. On the other hand, it is also true that using multiple fragments, we use more hash functions, so mitigating better the impact of collisions. So the question here is really, what is the best trade-off among the two? Our goal is to optimize the fragment update policy, and we think that in general, this should take into account different traffic loads on the different device. For example, consider this toy case where a traffic source generates a packet and we choose to count the packet only on the first switch. Maybe this can be a good choice if the switch 2 is highly overloaded. We validated our intuitions with the testbed topology and we implemented the setup in the OMNet++ simulator. As you can see here, we consider a bus topology of 8 switches with a simple traffic scheme that allowed us to study the effect of counter pollution. So here we have two classes of flows that for simplicity we name horizontal and vertical flows. And we vary the parameter KH, which is a random subset of switches updated for horizontal flows. Of course, vertical flows cross a single fragment, so we have no choice. And by changing K, we are essentially able to control the counter pollution on the sketch fragments. And we just evaluate the average relative estimation error, which is the error normalized with respect to the true flow size. Please note that in the count mean sketch that we have considered, since we always add the one during the update operation, there can be only overestimation errors. And here is the numerical evaluation. On the left, you can find the global average relative error. On the right, instead, you can see the breakdown by the two categories, vertical and horizontal flows. And as you can see, there clearly exists an optimal trade-off between the number of estimators and the counter pollution. So in order to conclude, we have seen that disaggregated sketches offer a new methodology to the design of network-wide measurements. However, a clever update policy that considers traffic patterns in the network is still lacking. Through numerical simulation and under a simplicistic testbed scenario, we showed that there should be an optimal update policy capable of selecting a subset of fragments to update. In our group, we actually have already derived a refined analysis for finding the optimal number of updates for the simple bus topology scenario, and we're currently getting quite good results, and we are extending to a more general fat tree case. So I invite you to stay tuned, and thank you for your attention.